Welcome to today's paper reading. Today's paper is titled, Adaptive Retrieval Augmented Generation for Conversational Systems. This paper was published on the AR14 preprint by Wang and colleagues from the University of Sheffield and University of Liverpool. The abstract discusses the integration of Retrieval Augmented Generation, RAGate, in conversational systems, highlighting its effectiveness but also questioning its necessity without explicit control. The study introduces RAGate, a gating model developed using human judgments to determine the need for RAGate in each system response. Extensive experiments were conducted, showing that RAGate effectively identifies appropriate RAGate usage for high-quality responses and high generation confidence. The study also found a correlation between generation confidence and the relevance of augmented knowledge. Large language models, LLMs, have significantly improved conversational systems, enabling the generation of natural and high-quality responses. However, recent studies have identified several limitations, such as the lack of up-to-date knowledge and the generation of non-factual content. To address these challenges, a common approach is to retrieve and augment LLMs with external knowledge. For instance, using a dense retrieval model can significantly reduce the hallucination rate. Similarly, leveraging a graph-structured knowledge base can boost the reasoning ability of conversational agents. To further enhance conversational systems, we propose an adaptive retrieval augmented generation solution with a binary knowledge gate mechanism called RAGate. This mechanism efficiently uses external knowledge at appropriate conversation turns, producing high-quality system responses. Figure 1 illustrates a conversation where responses are generated with and without the use of a knowledge snippet via a language model, specifically GPT-4. The example highlights how the inclusion of external knowledge affects the system's response, showing that while knowledge-augmented responses can be more information-rich, they may also limit diversity and assume specific user preferences. Conversely, responses without augmented knowledge appear more diverse and natural, especially in the early stages of a conversation. This comparison underscores the potential drawbacks of misusing external knowledge in conversational systems, emphasizing the need for adaptive augmentation strategies. In the field of knowledge-augmented generation for conversation systems, two primary components are crucial: the knowledge retriever and the response generator. Previous research has focused on enhancing these components individually or jointly to improve conversational responses. For knowledge retrieval, studies have utilized dense passage retrieval techniques and public search services. For instance, Li et al. 2022 employed TF-IDF and cosine similarity for ranking retrieved Wikipedia passages. Kameli et al. 2022 transformed dialogue context into a search query using an encoder-decoder model. Joint optimization approaches have also been explored, such as Shi et al. 2023, who introduced a dual feedback mechanism to improve task-oriented dialogue systems. Shin et al. 2023 proposed a training method based on maximum marginal likelihood to optimize both the retriever and generator. Additionally, the necessity of augmenting every conversation turn with external knowledge has been questioned. The knowledge-seeking turn detection task, using the DSDC-9 dataset, aims to identify turns requiring external knowledge, highlighting the need for adaptive use of retrieval augmented generation in advanced conversational systems. Figure 2 illustrates the three different variants of RAGate designed to implement the gating function in conversational systems. The first variant involves prediction using pre-trained language models after prompting. The second variant uses parameter-efficient fine-tuning with QLORA to adapt the language models. The third variant employs a multi-head attention encoder to model the context and estimate the necessity for knowledge augmentation. Each variant is tailored to enhance the adaptive use of external knowledge in generating system responses, ensuring they are contextually appropriate and relevant. The study defines the task of user-system conversation as a set of dialogues D, where each dialogue D comprises a sequence of interactions between users and systems. The conversational context up to turn T is formulated by aggregating previous interactions. The study introduces a binary gate mechanism to decide when to augment the conversation with external knowledge, dynamically updating the response generation based on this decision. 3 RAGate variants are explored: RAGate Prompt, RAGate PFT, and RAGate MHA, utilizing large language models and multi-head attention with parameter-efficient fine-tuning and devised prompts. Table 1 presents the retrieval performance evaluation when using context as the query. The table compares the performance of two retrieval models, TF-IDF and BERT-Ranker, in terms of recall at 1 and recall at 3 metrics. The TF-IDF model shows a recall at 1 score of 0.0227, while the BERT-Ranker achieves a higher recall at 3 score of 0.4714. This indicates that the BERT-Ranker model is more effective in retrieving relevant knowledge snippets when the context is used as the query. The dataset used for training and evaluation is KITAD, which includes 5,324 dialogues, 52,063 turns of conversation, and 33,761 knowledge snippets. For model implementation, Llama v2-7b and Llama v2-13b are employed, with QLORA using the PFT library and a lower rank set to 16. Evaluation metrics include recall at 1 and recall at 3 for retrieval performance, as well as precision, recall, F1, and BLEU, Ruizhe, and BRT scores for response generation effectiveness. In this section, we present the results and analysis of our RAGate methods. We evaluated the classification accuracy of RAGate variants, including RAGate Prompt, RAGate PFT, and RAGate MHA. The highest F1 score achieved by RAGate Prompt was 0.1230, while RAGate PFT reached 0.4082, and RAGate MHA showed a recall of 0.5835. We also analyzed the impact of augmentation on model performance, observing significant precision improvements from 0.5203 to 0.6818, but with a drop in recall from 0.3359 to 0.2321. The inclusion of knowledge snippets led to a performance drop, indicating added complexity. Lastly, we evaluated the effect of adaptive RAG on response generation, noting improvements in BLEU, Ruizhe, and BRT score metrics, ranging from 10.54 to 16.05, 0.8142 to 0.8259, and 9.3642 to 9.0655, respectively. Table 2 presents the classification performance of RAGate baselines evaluated on the KITAD dataset, which includes rich human labels on the use of RAG for response generation. The table details the precision, recall, and F1 scores for different RAGate model variants, including RAGate Prompt, RAGate PFT, and RAGate MHA. It also explores the effects of using synthetic responses and recognized name entities in the fine-tuning process. The configuration of the number of heads, layers, and embedding size for the best-performing models is highlighted, providing insights into the optimal setup for adaptive knowledge augmentation in system responses. Table 3 presents the results of applying RAGate to the KITAD model for adaptive knowledge augmentation. It shows that RAGate MHA outperforms RAGate PFT and effectively captures the trend of augmentation needs. The adaptive augmented response generation with fewer knowledge snippets results in a higher confidence level than Augustall. Additionally, RAGate enables the conversational model to maintain a high confidence level and ensure faithful responses, with RAGate MHA only lowering the average confidence score by 0.36% compared to 1.65% for random selection. Figure 3 illustrates the frequency of adaptive augmentations concerning the position within a conversation. The analysis is conducted across various conversation positions and domains within the KITAD dataset. The RAGate PFT, Conx-, SYN-RESP, NA, and RAGate MHA, Conx, models, representing high precision and overall best performance respectively, are used for comparison. The figure shows that the majority of human augmentation selections occur at the beginning of conversations, a trend effectively captured by both RAGate approaches, particularly RAGate MHA. This phenomenon can be attributed to the semantic coherence of conversations. Once sufficient additional information is provided early on, the value of knowledge augmentation diminishes for subsequent turns. Figure 4 illustrates the frequency of adaptive augmentations across various dialogue domains. Notably, domains such as travel, hotels, trains, flights, service, and rental cars show higher augmentation frequencies, indicating a greater need for additional information to assist in suggestion making. The RAGate MHA model effectively aligns its selections with human preferences, while RAGate PFT tends to present fewer augmentations, with the exception of the travel domain. This analysis highlights the differences in augmentation strategies between the models and their impact on domain-specific dialogue responses. The study investigates the utility of retrieval augmented generation in conversational systems. The proposed RAGate functions effectively identify augmentation needs and capture human preferences, particularly in the early stages of conversations. RAGate also aids in suggestion making and description enrichment. Experimental results indicate that RAGate ensures the quality of generated responses and enhances the system's confidence in producing faithful outputs, especially when relevant knowledge snippets are used appropriately. However, the study has limitations, including the use of only a few retrieval techniques like TF-IDF and BERT-Ranker, the inability to use larger language models like GPT-4 due to computational constraints, and the lack of extensive conversational data for evaluation. These limitations highlight areas for future research. Thank you for watching.